then what I want to do after that is do a presentation. So I'm going to present. I'm going to present my screen. And here's my screen to present. So I'm going to share it and all that good stuff. Okay, so hopefully my slides are popping up there, and maybe they're not on the full screen yet, but I hope they do become on the full screen when I hit this from this location. So you should see my slides in the full screen and me in the little side screen if you're out there watching in space. So this is where we had ended our time together on Monday. And this was a discussion of light. And again, I will probably say that many of you maybe talked a little bit about the behavior of light in if you took Physical Science 101. Our idea with light is to look at how light interacts with matter and the interesting aspects of light interacting with matter. And I pointed out at the end of our time on Monday, near the end of it anyways, that it was light that allowed scientists to unravel the structure of matter. Again, we can't really see atoms, we can't see subatomic particles, and all information we learn about them was kind of secondhand. And it was secondhand information gained by shining light on atoms and molecules. And it was the reaction that the atoms and molecules took when light strikes them that allowed us to now understand the behavior of light. Now, one thing you should recognize immediately is that anytime you shine light or anytime you see light, it is passing through matter because we live in a world that is full of matter. So at all times, light as it moves through space is in some way encountering matter. So we're going to discuss the various ways in which light encounters matter, and we're going to discuss what occurs when light encounters matter. And as a matter of fact, a wide variety of things can occur when light encounters matter. But what we were discussing at this juncture on this slide was the fact that light more generally is called electromagnetic radiation. And that's because what light actually is a propagating electric and magnetic disturbance through space. Through what we call space, or the void, or this thing that we live in, light passes through space as an oscillation of a magnetic and electric field. The electric field, if you like, will change sign from plus to minus, from plus to minus. And then it makes like a peak and a trough of a wave as it does that, if we want to relate it to something we're familiar with, like a water wave. Simultaneous to the electric field oscillating from plus to minus to plus to minus, what happens in the world of physics is that changing electric field makes magnets. So simultaneous to that, we have a north to south magnetic field, or action of the magnetic effect through space. So they just constantly are regenerating each other. Plus to minus electric, or north to south magnetic, and they just move and move and move and move. Now, in this bizarre thing that we call space, they just continue to move. As long as there's no matter in the way, light will literally go forever. Now that's a bizarre concept in its own right, but once you start the oscillation of space with electric and magnetic fields, it continues forever. Now, forever sounds like a concept that who can believe that anything can last forever? Well, I can offer very simple evidence to you that once you start light, it doesn't stop unless it encounters matter. When light encounters matter, then it can be stopped. And I think we all know that. If I shine a flashlight at the wall and you're standing on the other side of the wall, you do not see the flashlight. The wall, as we would say, absorbs the light. Well, the wall actually does other things too. It reflects the light as well. But ultimately, if you're standing on the other side of the wall, it has absorbed the light that is attempting to pass through it, and the electromagnetic wave ceases. Now, where does the energy of that wave go? Well, the atoms and molecules in the wall have absorbed that energy, and they took that energy up. What is the result of those atoms and molecules in the wall taking up that energy? Well, let's try to answer that question as simply as we can. It's a really fascinating story if you stop to think about it. So we're going to try to answer the question as to when I shine light on a wall, where does light go? And what about the conservation of energy and all these other things that have to be obeyed in our universe? So the story of the day then will be light interacting with matter. But before we get there, again, let me return to this point that I made earlier. If there is no matter and light is somehow generated, nothing stops it. It goes and it goes and it goes and it goes, and it literally will continue forever. Now, again, how do we know that? All you need to do is go outside at night and look up. And the things you're seeing are bright points of light, but the location of the source of the light emanating from those points is so far away that we don't even understand. There's no way to comprehend how far that light has traveled so that you can see it coming to you. Now, you have to remember, it came through a lot of atmosphere. There was a lot of empty space from where that light started to it reaching you here on Earth. A lot of empty space. And it had no problem just doing its merry electromagnetic dance through that empty space. Finally, and I'm talking finally after thousands, if not millions, if not even billions of years, as that light did the dance, it has made it here. But before it can come down to the Earth or make it to your eyeballs that you can see, it has to pass through a huge amount of matter. There's a lot of atmospheric molecules that now begin to tug and pull on the energy of that electromagnetic radiation. And if the frequencies of the radiation are just right, they get removed by that matter as the light impinges on it. So again, this is some of the story that we're going to be discussing over the course of the day. Now, before we get into it more deeply, again, I want to point out some of the characteristics. Let's take a look at the wave that I'm showing on the slide. There's three important characteristics of this wave to recognize. First is the amplitude. That is the vertical displacement from the 0 point. The line in the middle would be, if you like, flat. That would be the surface of the lake. When I drop the wave, the surface of the lake undulates, and then you have a crest and a peak, a crest and a trough. And the amplitude is the distance above the surface or the distance below the surface. Now, we're going to assume, and it's a good assumption, that the amplitude in the plus direction is exactly equal to the amplitude in the negative direction. So the peak is just as high up as the trough is deep for the undulation of the surface. Now, the traveling of the wave, though, is horizontal. Just because the disturbance is vertical, the surface is moving up and down. As the surface moves up and down, the wave moves horizontally. So it's kind of bizarre, but think about that's what a water wave does. The surface vertically disturbs, but the wave moves forward towards the shore. So it's the same kind of idea here. Now, that is another idea to keep in mind. A wave, in many ways, is a disturbance. You need something for the wave to propagate through to disturb. And in water, it's quite obvious. You drop the rock and it disturbs the water medium through the air as I'm talking to you. What is happening is I am pushing air molecules and creating pressure differences in the air itself. And that is generating literally a wave of air disturbance that is wiggling through the air in this room, coming down your ear canals and beginning to wiggle little membranes in your ear that push on little bones in your ear, that stimulate little nerves in your ear, that make little electrical signals in your ear, which go into your brain, and you translate into the word brain. Okay, so there's all kinds of wave action that is going on to make these sorts of things happen. Generally, waves need a medium to propagate in, meaning the next time you go to the Star Wars movie and they're in space with riding in the Millennium Falcon, they don't even have that anymore, do they? See, that's when I watched the first three and they were still driving the Millennium Falcon. I don't even think they do that anymore, do they? I don't know, whatever. But anyway, when they were driving the Millennium Falcon in space, you should stand up and say, "Stop the movie! Stop the movie! You can't hear in space. There's no sound in space. There can't be sound. Because unless there's a medium for your burst of air pressure to wiggle, there's no way for the sound wave to get to your ear canal." So generally waves need a medium to propagate in. Light is weird though. The medium of light is space itself. It's this weird stuff that we are in. And it literally disturbs the space, changing its electric and magnetic characteristics. If there's matter there, that messes with the light. It starts to do various things to it, as we will see. So really, light prefers no matter, but when it encounters matter, it starts changing the properties of the matter, and it starts changing the properties of the light. Okay, now, there are two other things to discuss before we move, and that is wavelength. That is the distance traveled for one complete wave cycle. Now, I mean the complete cycle. So if I start at the top, I have to follow and trace the wave disturbance all the way through back to zero, down to the trough, back to zero, up to the next crest. As I'm showing between the arrows here. If I want to find the wavelength, I have to go one complete cycle. And another thing we're going to remember is that all the wavelengths are going to be the same. Meaning I could measure this wavelength from crest to crest, or trough to trough, or starting point on the way up to starting point on the way up. However I want to measure it, they will all be the same length. So you would need a measurement in length to get a wavelength. And we would typically use meters, if you like, or something like that. If you're going to talk in the SI world, we would measure the length of this in meters. But meters are big. Meters are like as big as a yardstick. That's too big for light waves. So we usually use some metric prefix to change the scale on which we measure light. Typically, we measure in nanometers, which is billionths of a meter, very tiny little lengths because of the fact that light is such short wavelength. Okay, then one last thing is this word below the picture. It says the frequency of light, and we equally often talk about light in terms of its frequency. And frequency means if you stand still and the wave is traveling by you, how many complete waves go by per second? That's the frequency. The shorter the wavelength, the more the waves go by per second. Okay, now finally, after all that, frequency is symbolized by the Greek lowercase v, which is kind of like the Greek n, actually, believe it or not, and wavelength by the lowercase Greek lambda, which is the lowercase l. And it turns out that these quantities are exactly inversely proportional. Okay, now What do I mean by exact inverse proportionality? If you cut the wavelength in half, you double the frequency. Now, you should easily be able to understand that. Wavelength is how long it takes to go one complete cycle. Let me make the waves half as much space to go one complete cycle. And the wave is zooming by me. Well, if they're half as long, twice as many go by me every second. So if I cut the wavelength in half, I will double the frequency. And the opposite, of course, is just as true. If I make the waves longer, make them 4 times as long, then it will take them 4 times as much time to get by me. So 1/4 of them will go by me in the same time period. So when the waves are 4 times as long, the frequency of the passing of waves is 1/4 as many per second. So these are exactly inverse proportional. You take one up by a number x, the other one goes down by 1/x. If you make the waves 10 times bigger, 1/10 as many can go by per second, and vice versa. So I can make these little arrows and show when the frequency goes up, the wavelength goes down, and vice versa. Now, it turns out that these are connected phenomena. All electromagnetic waves experience this change in frequency and wavelength, but they're all to the same proportionality. So if you multiply the wavelength times the frequency, you always get the same number for any wave. Take its frequency times wavelength, and it always comes out the same. And the magic number that is the product of multiplying the wavelength times the frequency is maybe the most important number in science. And that important number in science has a name that probably your mom and them know. It's called the speed of light. C is the product of the wavelength and frequency, and it is the speed of light, and it's the same for all light. Now, what do I mean the same for all light? Red light, zooming around the room. Orange light, yellow light, green light, blue light. They all have the same speed of light. All of them. When they all come out of the sun, all these colors are coming out of the sun mixed together perfectly. And when they reach the earth, they all reach the earth at the same time. So all of them get here at exactly the same time because they're moving at the same speed. Now, what makes red light different than orange light or yellow light or blue light? Simple thing that makes them different is their wavelength or frequency. Pick one, and that's what it is. When you say Roy G. Biv, red, orange, yellow, green, blue, violet, those are the segments or the individual colors of the visible light spectrum. Well, you're saying them in order from lowest frequency to highest frequency. Red is the lowest frequency light. Orange is a little higher in frequency than red. Then if you make the light a little higher frequency, it turns from orange to yellow. If you make the light a little higher frequency, it goes from yellow to green, and then from green to blue, and then finally from blue to violet. Well, what happens if you make it higher frequency than violet? Then we can't see it anymore. And we call that ultraviolet. You make it too high in frequency, the built-in mechanism we have to see can no longer detect it. And now it is in the regime called the ultraviolet regime. So again, these go upward in order of frequency. Low frequency at the bottom, high frequency for the violet. Okay, now if you want to think of it in terms of wavelength, though, it's completely opposite. When the frequency gets short or higher frequency, excuse me, more waves pass per second, that means the waves are shorter. So I said the highest frequency color is violet. That means those are the shortest wavelength colors. I said the lowest frequency visible light is red. That means these are the longest waves. Red light and orange light are exactly the same in terms of changing electric and magnetic fields. The only difference is that red light is lower frequency than orange light, meaning red light has a longer wavelength than does orange light. That's simply all it means. So the speed of light, which is I'm going to represent by C, is a constant for all frequencies and wavelengths of the electromagnetic spectrum. Okay, so let's say some more things about the speed of light. We said this already, those things are inversely proportional, and the proportionality constant, or the thing that makes them equal, is this value C. And this number is very important to us, so it has been measured very carefully. And this is the speed of light as best we know it, to like 9 digits of accuracy. 2.9979245 times 10 to the 8th meters per second. That is very precisely measured. Somebody spent a lot of time and effort to make that measurement. So this is how fast light goes in a vacuum, as it says here. Now, I hope we understand what it means to be in a vacuum. That means no matter present. When you're in a vacuum, you never encounter a molecule or an atom. You're just going through pure, empty space. Now, really, to us, that's kind of a bizarre concept. Why? We are never in a vacuum. Never in a vacuum. If we were in a vacuum, first of all, we wouldn't be able to breathe. But even worse than that, our internal pressure, we are kind of held into our shape because of many forces. And one of them is the fact that there's air pushing inward upon us that helps us maintain our shape. If we were in a complete vacuum, unfortunately, what would happen is we would explode, because our internal pressure would be so greater than our external pressure that we would just begin to be pushing outward on our skin until it just shredded. Not a very pretty thing to think about, but that's exactly what would happen. So we really don't have much experience with a vacuum for very good reason. But if light is not around matter, which, believe me, most light is for the vast majority of its time. Why? Because when it's generated by a star in space, there's generally no atmospheres between the points where those stars generate that light and where they ultimately end up. Very few planets that they strike have any atmosphere at all, so many of them get all the way to the surface of them if they do encounter planets at all. So a lot of light just flies around this universe through a vacuum, more or less, never encountering any matter anywhere, and it would move around at this very carefully measured speed. Remember, I talked about some of the aspects of that when we have a number known to this accuracy. A lot of care was made to measure that number because it is such a very important number towards the behavior of our universe. Okay, so when light goes into any matter, it slows. And the more dense that matter is, the more there's a decrease of that speed of the matter. Now, this word dense that I'm using here is a little bit different than normal density of measurements, but it says something about how the molecules in a substance interact with the oscillating electric and magnetic field that is passing through them. Remember, atoms consist of charges in motion. Charges in motion make their own little electrics and magnetics. So the electric and magnetic inherent to the structure internal to an atom can now begin to interact with the electric and magnetic of this passing wave. And if they happen to match very well with each other, then they work together. Now, what I mean by that is, let's suppose I have my kid sister on a swing. And I start pushing my kid sister. I can increase my kid sister's energy by routinely pushing her back and forth on the swing. Now try to relate that to a periodic wave motion, and that's exactly what it is. We can say the 0 point of my kid sister's swing is when she's just sitting there without me pushing on her. So that's the 0 point. So now she starts to fly one way past that 0 point, comes back to the 0 point, and flies the other way to a maximum. So she goes 0, maximum one direction, back to 0, maximum other direction. So the motion of a person on a swing is much like the motion of a wave. And now think of me pushing her on this swing. I am providing the energy to make her ride her wave pattern. If I quit pushing, then she doesn't maintain her wave pattern. Her friction with the air and the friction of the strings of the swing make her eventually slow down and stop. So I must constantly feed her energy to keep her in the swinging pattern. Now, the same thing can be said with atoms in a substance and now light impinging on that substance. The light comes by with a certain frequency of its electric and magnetic fields. The electrons are moving, if we think like Rutherford, they're moving like planets around the nucleus. If the frequency of the light is just correct, it smacks into the electron just right every time on the way around and can keep the electron excited at a higher energy point than it would be without that light. Now, as crazy as that sounds, that's what you see all the time when you see color. If you see colors, it is due, of course, to a dye molecule in some material. But what is that dye molecule doing so that you see the green of my shirt? Because the light that's actually striking my shirt is not green. The light that is striking my shirt is all colors. So all colors come from light sources, not all light sources, but typical ones that we use. All colors come out of them, and only certain colors come back to you from that. All colors are hitting me, but you're only seeing green when you look at me. So there's some interaction between the light that comes to me, the dye molecules in me, and what happens when the light returns to you. So this is some of the issues that we're going to be straightening out on the upcoming slides. How does this process work, and what are we seeing when that process occurs? Now, again, I want to keep you to keep in mind that when light encounters matter, it's no longer going to be moving at this top speed. The top speed of light is 2.99792458 times 10 to the 8th meter per second, as fast as it can go. Now, one last point I want to throw in there. This is the speed limit of the universe. Nothing in the universe can go faster than the speed of light. And I tried to mention that last time. When things reach the speed of light, bizarre stuff starts happening to them. Time dilation, length, dimension stretching, mass increase occurs. All kinds of weird stuff happens if we could get towards the speed of light. Okay, so let's, what else do I say here? Okay, all forms of electromagnetic radiation, I keep hammering this home, they all move at the speed of light. So red light goes at the speed of light, so does orange light, so does green light, so does purple light. They all move at the same number. Okay, so let's look at the so-called electromagnetic spectrum. I'm going to start at the long wavelength end or low frequency end and move to the right to the short wavelength end or the high frequency end. Now remember, wavelength and frequency are inversely proportional. Wavelength is one complete oscillation of the wave. Frequency counts how many waves go by per second. So when the waves are long, they're low number going by per second. When the waves are short, there's a large number going by per second. So these two numbers are exact opposites of one another, but they're both commonly used to measure properties of light. So I'm including them both in this discussion. Okay, so now I'm going from, if you like, from right to left to increase my wavelength. I'm going from left to right to increase my frequency. Then it starts down at the bottom. We would have the things we call AM stations. Now, what kind of wavelengths am I talking about for AM stations? I'm talking about football fields of length. To complete one oscillation of electromagnetic radio waves, you have to start at one end zone and then go up, 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 back to zero, down, 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 back to zero, a couple football fields later. So we're talking incredibly big, long wavelengths when you talk about AM. If you shorten that wavelength down, you come to FM or television frequencies. If you shorten that wavelength down even more, you come to the so-called microwave regime. Even more, you come to the radar regime. Even more, you come to infrared. Now, if I shorten it even more, I come to finally the visible. Then I hit the ultraviolet, the X-ray, and the gamma ray. Now, I want to point out to you, all of these you have probably heard the name of, one place or another. All of these are exactly the same in terms of what they're composed of. They're composed of oscillating electric and magnetic fields. The only thing that makes one different from the other is the frequency or wavelength that the waves are operating under. As you move to shorter and shorter wavelengths, you go from left to right through these various components. Now, are there sharp cutoffs between, say, microwave and radar and infrared? It's really, there's a number that they assign to where the cutoff is, but it's really not very different in terms of what it really boils down to being. It's just a change in how long the wave is as we move through this pattern. Okay, now some of these, I shouldn't say some, pretty much all of these have uses in modern technology. We use electromagnetic radiation up and down the board. Many of them you can recognize right away and pick out the common uses of them, like radar. I think we can figure out the common uses. Microwave, I think we can figure out the common uses. And even things we call AM radio waves, I think we can figure out what we're using those for. X-rays, we know are familiar with. Now, gamma rays, a little bit weird, maybe. Ultraviolet, maybe a little weird. But all of these have various uses, particularly in science, for sure. But most of these have uses commercially as well, as I'm sure we're very much aware of. One of the things I want to point out to you is the interesting story of the microwave. And of course, now every home has a microwave, and we use a microwave to cook stuff. Now, it's nowhere near the conventional cooking that we use in terms of like an oven. It has completely different properties. What an oven does is heats the molecules in the oven chamber, and those as they gain heat energy from the oven itself, they move around faster and faster and faster. And as they move around faster and faster and faster, they slam into the turkey that you put in there and they cook it. That's literally what's going on. You're putting energy into the air in the oven, and the air molecules in the oven impart that energy into the turkey, and hit it with such forces that they invoke chemical change in the turkey. Now, a microwave does it completely different. The air in a microwave doesn't get hot. Now, you might feel a little steam coming off the cup of coffee you put in there, yeah. But that's the water vapor coming literally out of the coffee. The chamber itself, you are not feeling any effect of heat in the air molecules in that chamber. That's because the chamber is designed so that the air does not absorb the microwave frequencies. Air is mostly nitrogen and oxygen. They don't absorb up microwave. However, water molecules love microwave. They love it. Water molecules suck up microwaves and it makes them dance. And if they're close to each other as they're dancing, they're rubbing. And if you rub your hands together, I think what you can feel is a large amount of heat built up in the friction of attraction between your hands as you rub them. Much the same way when you have water molecules in close proximity, say in a cup of coffee or in a frozen burrito, and you hit the microwaves on them, the microwaves are just the right frequency to make the water, the electrons and water molecules themselves dance. And they start picking up and scooping up that energy, just like my kid sister on the swing. And as they pick up and scoop up that energy like my kid sister, they rub into each other and generate heat within the cup of coffee. So microwaves cook in a very different sense than do conventional ovens. They cook using electromagnetic radiation, whereas regular ovens cook using what we call convection, or just transfer of energy from molecule A into molecule B, into molecule C, into molecule D. Okay, now the other maybe interesting thing before we move is that when the military began looking at using radar, they didn't use radar because it turns out microwaves are easier to generate. We have electric circuits that make microwaves very powerful and very cheaply. So they knew how to make really good microwaves, and they thought they could do the same thing that you do with radar with microwaves. But like I said, microwaves are loved by water. So when the military started shooting microwaves at airplanes in the sky, they weren't getting any signal back because the water in the air was absorbing the microwaves. They moved the frequency to radar, and the water molecules now said, we don't like that because they don't stimulate our motions the way that microwaves do. So the radar can go right through the water in the air and bounce off a plane and come bouncing back to the military, and they can gauge from the time it takes the microwave to get, the radar wave to get there and back. They can tell how far away it is, and they can tell how fast it's moving. So I'm sure we're familiar with the concept, or at least we know of what radar is used for. It's used for speed detection, and it's used for speed detection mainly because when you shoot it through the air, it doesn't interact with the air like microwaves do. Microwaves get absorbed by water and transfer energy into water. Radar waves don't get absorbed by water, and they just fly right through and bounce off whatever they impinge on and come back. Okay, now I have another cartoon here trying to show what happens to the wavelength. Now this is not to scale, but I'm trying to show you you see in pink or written in the gray, there's a picture showing an oscillation of light through the gray. And you'll notice as we go from radio down to microwave, down to infrared, that the waves are getting shorter and shorter and shorter in wavelength. Until you reach the gamma end of it, the wavelength is really tiny. Once again, I want to point out these are not to scale. They're just trying to cartoon represent what happens to the wavelength as you go from the left to the right in the electromagnetic spectrum. Now you'll notice there's a very little skinny spot that has been expanded, and that is called the visible range. So the part of light we see out of the total electromagnetic spectrum is only a small portion of the electromagnetic spectrum. Your eyes do not work very effectively in seeing all the light around us. We don't see any of the infrared. We don't see any of the ultraviolet, any of the microwaves, radio waves, X-rays. We don't see that stuff. Our eyes are not built to detect radiation in those frequencies. Our eyes are only built to decipher and decode the very small segment that you see between, as we say there in nanometers, 700 nanometers and 400 nanometers of wavelength. And the NM is nanometer. That means billionth of a meter. So what you're supposed to take from this picture, we only see a very small portion of the spectrum, very small. Most of the electromagnetic radiation we don't even see. And believe me, in this room right now, there is electromagnetic radiation of basically every one of these frequencies flying around this room. Just think of how many radio stations when you get in your car you can tune to. You don't think they're flying through this room right now? All of those radio stations are moving right through this room. All the FM, all the TV, all those signals, the thousands of airplane communications and all these other things, they are zooming through this room right as we speak. They're just not in the visible regime. Now, all the other ones are as well, I will tell you. The sun emits all these wavelengths and frequencies. And not only does visible light come crashing on Earth from the sun, all these lights come crashing on Earth from the sun. Now, maybe a point of interest. Remember, we're pretty far away from the sun. Good thing. If we weren't, as a matter of fact, I should more correctly say, we're perfectly far away from the sun. If we were much further away, plants wouldn't grow as effectively as they do. If we were much closer than we are, plants wouldn't grow as effectively as they do, and neither would our atmosphere have been able to stick onto the planet as well. So we're about perfectly far away from the sun for life to flourish on the Earth. But that distance is about 93 million miles. And once again, that's a number that hardly makes any sense to us in terms of just trying to think about how far away that is. It's pretty darn far. We'll just say that. We are 93 million miles away from the sun. Pretty much there's a complete vacuum. There's no atmosphere until you get to the only a mile above the surface of the Earth. That's anything above further than that. There's very, well, okay. When you get to the top of Mount Everest, which is about 3 miles up, there's still atmosphere. So, okay, we'll go 5 miles up. By the time you get 5 miles up, you're pretty much out of the atmosphere of the surface of the Earth. So the light that comes from the sun doesn't even start to hit any matter until it's 5 miles. It made a 93 million mile journey, and the last 5 miles, it starts encountering air molecules as it comes crashing to the Earth. Well, the other thing I want to point out is I told you the speed of light. I gave you those numbers earlier. When a light beam is generated on the sun, it takes it 8 minutes to get from the sun to the Earth. So that's traveling a long way. 93 million miles, and light moves so quickly that it can traverse 93 million miles in 8 minutes. So if somebody turns off the sun, you still get 8 more minutes of it before that effect of the sun turning off actually will make it here to the Earth. Interesting though, if you turn off the sun's gravity, it's instantaneous that we will no longer feel the pull of gravity. Pretty cool idea, but that's a story maybe for another time. All right, so what else do I want you to know or recognize from this slide? The bottom underneath the bar graph that's on there not only says something about wavelength, it has some numbers, it says something about energy, and that is something that is very important. The long wavelength, low frequency light is low energy. The short wavelength, high frequency light is high energy light. Now, what makes that so important is that when we start to get around radiation that is too high in frequency and we're around it too long, it can damage our makeup, meaning the matter that makes us up being struck by light of too high of a frequency is putting too much energy into us, and that ain't good for us. So if you look below the visible regime, you see radio waves, microwaves, infrared. These things are more or less harmless towards human tissue. Then, of course, visible light we know all about, but I want you to notice what's above the visible light. Once you get above visible, which means you're to wavelengths that are shorter than you can see with your eyes, we begin to call that ultraviolet. Then you move into X-ray. Then you move into gamma ray. Those three, in case you're not aware, you don't want to be around those too long. If you're around ultraviolet stuff too long, you get sunburned. And if you stayed around it too long, you wouldn't be in good shape, okay? It would frazzle you. Long enough exposure to too much ultraviolet, not a good thing. I think we also know that X-rays, even technicians that work in the X-ray field, they have to be very careful about how much X-ray they are exposed to. Gamma ray, that's really not quite as familiar to us as the other two, but that's, as you can imagine, even more lethal. We get around too much gamma ray, we wouldn't last very long at all. This is one of the kind of things that is emanating out of nuclear bombs and things of that sort. So, again, energy goes along with frequency. The higher the frequency, the higher the energy. The lower the frequency light, the lower the energy. One last time before we leave this, I want to point out these all travel at exactly the same speed. Radio waves, microwaves, infrared, visible, X-rays, all go at the speed of light. These are across the board being generated by the sun. So the X-rays from the sun take 8 minutes to get here. The infrared from the sun takes 8 minutes to get here. The ultraviolet from the sun takes 8 minutes to get here, just like the visible light takes 8 minutes to get here. So one thing I guess we should also take from this, I said that the ones above visible are harmful, but the sun is outputting them all the time. So we are being exposed to ultraviolet from the sun. As a matter of fact, you got to be careful. If you go to the beach, you better put on your UV block because you might get too much UV at the beach. We're being exposed to X-ray by the sun. We're being exposed to gamma ray by the sun. But it turns out our atmosphere and other components around us are really good at eliminating most of the X-ray, most of the gamma ray. So that's taken care of us by the umbrella which covers the Earth that we call our atmosphere. The atmosphere was also designed to take care of most of the UV, but it turns out we poked holes in it. You might have heard of the story of the ozone layer. And a lot of people made a lot of fuss about how we're destroying the ozone layer. The ozone layer is the umbrella to the Earth to protect us from UV. And we have drastically thinned that and even poked holes in it due to certain chemicals that have been released by human action into the atmosphere. So we got to be careful with what we do because there's been this delicate balance that has developed over time that has allowed life to flourish under the rules of the conditions that we have lived on this earth for 1 million years. We're changing some of those rules lately by what we are doing to the planet, and the planet's saying, wait a minute, we've been playing this game using these rules for thousands upon thousands of years. If you're going to change the rules, then there's going to be new outcomes. So we really do need to be careful about some of those things that might affect this delicate balance. And I want you to keep in mind this delicate balance which allows life to flourish on this planet. The conditions have to be oh so critically balanced for life to be sustained and occur. And we're still looking for it. I'm sure we'll find it eventually, but there's very few instances of it for all our looking around for it. Okay, all right, so let's talk a little bit about what waves look like when they go through space. And what we'll do is a familiar cartoon representation. If you throw a rock into the pond, you create a disturbance on the pond. You create a wave. And the wave emanates out circularly from the point of the disturbance. The further out you get from that point, the lower the undulations. Why? Because this is an energy disturbance. To push the water up and down takes energy. And so if you don't continue to feed the energy, then the wave dies out. So when I drop the rock, there's high energy at the point where the rock is dropped, but as the wave propagates horizontally, it's losing energy as it continues to try to move more and more water up and down. So eventually the ripples get smaller and smaller and smaller, and they die. Now the same thing is true. Let's take playing an instrument. Take one guitar string and pluck it. Burn. At first the noise is really loud, but as the string vibrates and moves air molecules that wiggle and wiggle and go into your ears and make sound, this oscillation of the string takes energy. And since you only plucked it once, you only put a fixed amount of energy in. And as the string oscillates and moves through space and through the air and has friction with the air molecules, it loses energy. So the sound dies. If I hit a piano key, ding, same thing. It oscillates the string, moves the air, wiggles my eardrums, and I hear sound. But the sound dies because of all the energy loss along the way. If I take a bow, though, and keep feeding energy, I sustain the sound. So by bowing the string, the sound maintains its amplitude, maintains its energy, but I have to continue to bow to continue to feed it energy. Kind of like my kid sister again. If I keep pushing her on the swing, she keeps feeding the oscillations. As soon as I quit pushing her, she dies out and comes back to the 0 point. So again, with the rock, I toss the rock in and it continues to feed waves out, but they eventually die out. Now, if I were to do the same thing with a light bulb, really what you should think now with a light bulb is the same kind of cartoon. Light waves come off of a light bulb exactly like they come off of the rock dropped in the pond. Meaning if I put a light bulb down in the center of the room and put us in a circular path around it, we would all see the same brightness of the light bulb as long as we're on one of these circumferences. So you pick a circumference, put all the people in the room on that same circumference, the light looks just as bright to everybody on that radial distance outward from the light bulb. Now, what if we move a further light bulb or a further circle back? Everyone on that circle will see the same light intensity, but the light intensity will be a little less. Why? Because the light is moving through the air. The air is interacting, the molecules in the air are interacting with the light waves, absorbing a little of it, and the light gets dimmer. Now, as I continue to make these concentric circles and get further and further and further from the light source, guess what? Eventually you can't see it anymore. Think about a flashlight way far away from you in the field. It starts looking dimmer and dimmer and dimmer, and you get far enough away, you can no longer see the flashlight because of the fact that the air between you and the flashlight has absorbed all the energy. So in that regard, it's like the pond. I drop the rock close to the point of dropping the rock. The undulations of the pond are greatest. And as I get further from where the rock was dropped, they're still coming towards me and still oscillating the surface, but they're diminishing in energy the further away I get. So these waves are also diminishing in energy the further I get. Now, if I put the bulb in a vacuum, if this is in a vacuum, there's no diminishing of the energy and the light remains just as bright the whole way on every circle. But it has to be in a perfect vacuum before that occurs. Okay, so until you put it in a perfect vacuum, there's going to be a decrease in the light energy because the molecules in the air are sucking on that energy and absorbing that energy. Now, what physicists like to do is put straight lines, and you'll notice the straight lines are perpendicular to all the surfaces of the circle. What we call this is something very familiar. It's borrowed from geometry. In geometry, if you have a ray starts at a point and goes to infinity. A line goes to infinity in both directions. A ray starts at a fixed point and then goes from that fixed point to infinity. So we call these light rays because in geometry, a ray starts at the point of the light bulb and then technically can go from infinity from the light bulb. So the light rays go straight out from the surface of the light bulb. Now, interestingly, they are all perpendicular on each circle. Notice how they maintain an intersection with the circle of 90 degrees, whether that's a circle in close, you go to the next circle, next circle, next circle, every light ray remains 90 degrees flat on the edge. Now, here's what's really interesting. As you go further and further out, the circle gets bigger and bigger, and the edge of the circle gets flatter and flatter, till eventually you make a big enough circle that looks flat. Now, of course, it's not flat, it's just a huge circle. Now, where do we see an example of that? Well, the rock we're standing on. We are standing on a huge circle. But when I'm playing on a football field, it doesn't look curved, it looks flat. That's because the Earth is such a huge circle that for all intents and purposes, its edge is flat. So as the circle gets big enough, all these rays are coming out perpendicular to the surface, but now they all are becoming parallel to each other because they're all just coming straight through the surface. So eventually, like for the sun, if you get far enough away, again, the circle gets flatter and flatter and flatter, all the rays start coming and looking like they're parallel. Now I'm going to back this up and I'm going to point out, or actually they should look like spokes. They should look like spokes coming from the axle of a bicycle wheel, because they start towards the center and then all spread out in different directions. But again, I will point out to you, and it sounds bizarre, but true. The bigger that circle gets, the flatter its edge starts to look. And then if you put the rays coming out of that flat edge perpendicular, they look like this. So when an object is sufficiently far away from the source, we say the light rays come in a light beam. We get a bunch of parallel rays all heading in exactly the same direction. Now, it turns out in practice, you don't really have to get that far away from the source before we can focus a light beam. Now, we cheat too. We make optics, we do tricks, like in a flashlight. Light is coming off the light bulb of the flashlight, but they put curvature and mirrors around it. And that bounces all the light in there and shines it collectively together into the beam. A car headlight, same trick. Really, all the light rays want to go in all directions equally likely, but we all know what they do. They put a curved reflective surface behind the light bulb. It catches it all just right, and it shoots it all out already pre-parallel. So we play tricks to make many beams parallel. But what I would tell you from the sun is 93 million miles away. Those light rays are naturally coming at us parallel when they're traveling those kinds of distances. So we have a light beam, if you like, coming from the sun because it is such a difference away. So we're going to generally talk about light rays in a beam more than we will talk about them in like bicycle wheel spokes. Okay, so when light hits matter, and I told you, all kinds of stuff can happen when light hits matter. Now, first, and I think pretty obviously, the light can go through the matter. And this is what we're seeing in this room. If the light wasn't going through the matter, you wouldn't see me. Okay, so, or I wouldn't see you. Light can go through matter. It just depends on the frequency and wavelength. Now, some of it is getting taken by the matter, and we just might not recognize it. The light is diminishing in energy and eventually will die out if it doesn't have enough intensity. But the light certainly can go through the matter. Second of all, light can be absorbed by the matter, meaning, again, once again, if I shine a flashlight at the wall and you're standing on the other side of the wall, you ain't seeing that light because the wall completely absorbs all the energy. And where does that energy go? It goes into the molecules of the wall. If you could look at their energetics, you've changed them. Now, if you put enough light energy into them, like a laser, you can literally put so much energy into those molecules that they begin to rip apart their attractions for one another, and you can blast your way through it. So typically the kind of light energies that we're impinging on objects, it just gets absorbed, and we can hardly even notice the difference in characteristics of those absorbed higher energy molecules in the wall. So light can go through an object, light can be absorbed by an object, but also light can do something we call spread. And scientists call spreading diffraction, and I'll try to show you a cartoon of what I mean by spreading light. Light can also be slowed, and when it slows, it bends. So light can be bent. Refracted means bending. Now, we use bending of light all the time. If you wear corrective lenses, even your eyeballs themselves, these are objects designed to bend light and focus it at a point. And this occurs when light is slowing down. When it slows down, it bends. Then light can be reflected. And what does it mean to be reflected? Literally bouncing off the surface. It hits the surface and comes off the surface so that it can make an image as it bounces off the surface. So we are actually familiar with all these things. We just might not have thought about the individual behaviors that light can do when it interacts with matter. Now, lastly, light can be scattered, and this is the weirdest of all. Scattered is a combination of 4 and 5. It's the midpoint between bending and bouncing. It shoots it instead of, I think we understand what bending does. It changes its direction. We understand what bouncing does. It sends it back in the direction it came from. Scattering kind of shoots it right along the surface without bouncing it and without bending it. So that's what we should think of. Number 4 is bending it. Number 5 is bouncing it off. Number 6 is kind of in between bouncing it off and bending it. It's shooting it right along its surface, sliding it along the molecule itself. And that's called scattering the light. Now, what does scattering look like? I have a cartoon here of a light wave coming down at a picture of a molecule. And what happens is the light is shot 90 degrees outward. Now, you need a large collection. There should be a big, large number of these water molecules. And it just slides right along the collection of them. when you scatter the light. It shoots horizontal if it was traveling vertically originally. Now that might seem weird, but this is a very important phenomenon to the behavior of our Earth. And I hope I have a cartoon that shows what that familiar phenomenon is, this number 6, and why it's so important. So let's see if I do have that cartoon. Oh, here it is. The eternal question. The eternal question that people have pondered, they originally pondered for centuries, was why is the sky so beautifully blue? Well, it turns out that the atmosphere that makes up the sky is 98% nitrogen and oxygen. Okay, what this would mean is about, if you take 4 molecules of air, 3 of them would be nitrogen, 1 of them would be oxygen, essentially. That's what these numbers are saying. Every 4 molecules of air, 3 are nitrogen molecules, 1 is an oxygen molecule. Now there's a smattering, you notice we add those 2 up, it's only 98%. What's the rest of air? Well, carbon dioxide, water vapor, argon molecules, a little radon, other pollutants that we put in there like sulfur trioxide, nitrogen dioxide, other things that come out of industrial processes. But the vast majority of air is nitrogen and oxygen. These are just the right size to interact with part of sunlight. So here comes sunlight 98 million or 93 million miles away from Earth. And it's flying through a vacuum for 93 million miles, and then it gets to the surface. Now I'm calling this the light from the sun white light. And we didn't really discuss what white light means, but white light means mixture of all colors equally. White light contains just as much red as it contains blue, as it contains green, orange, yellow, violet. Perfectly mixing all colors makes white. So white light is all colors mixed together, all moving at the same speed, all slamming into the atmosphere. When they do, the N2 and O2 molecules are just the right size that they shoot the blue. And the blue goes skidding sideways. So blue light is scattered from the sky and spread. When we look up, we're seeing the blue light being shot sideways. So when you look up, you're seeing blue light scattered off the nitrogen and oxygen in the atmosphere. Now, it's really not perfectly blue. It's kind of a little purpley blue. I think we're familiar with the word azure. It's the azure blue of the sky, which is a little towards the purpley blue, and that's the perfect light that is shot by the atmosphere of the Earth. Now, there are other planets, or even around here, that they claim that they would have red skies because of what most of their atmosphere is mostly methane. They would shoot frequencies so that you would see red when you were there if you could breathe it. But the Earth is scattering only the blue light in our atmosphere. Now, interestingly then, well, the oceans reflect the blue, so they look blue just because the sky is bouncing off the ocean. So that's a reflection phenomenon for why the oceans, a pretty ocean looks, or a sea looks pretty blue. All right, now, there's another interesting point about what that means. If the blue light is being scattered, what's left? Well, let's talk about the primary colors. The primary colors of visible light are red, yellow, and blue. And you can mix red, yellow, and blue and make everything else. So what we're saying is the blue is going sideways. What about the red and the yellow? Well, very interestingly, if you look sideways at the Earth, let's just put the sun coming at the Earth sideways, so that the blue light is being scattered from the sun, but now it looks like this blue light is being scattered horizontally. What happened to the reds and the yellows? Well, the reds and the yellows come down and land on Earth. But this phenomenon, you can only really detect it only when the Earth and sun are at just the right angle, so that you can detect the red and the yellow hitting the earth while the blue is being scattered somewhere else. And guess what the perfect times to do that are? There's two of them. The perfect times are either sunset or sunrise. And when you're looking at sunset or sunrise, you're seeing the effect of that red, yellow, orangish. Now, it depends on the atmosphere. It depends on the water vapor in the atmosphere and maybe even some pollutants in the atmosphere. Like they were saying right now in California, the skies look really, really red. And that's because of the ash and particles that are in the sky and mixed with this kind of phenomenon makes the sky look really red at sunset. So depending on what is in the atmosphere, the red and yellow comes to different degrees. You might see a little oranger, a little yellower sunset, a little redder sunset, but you're seeing the effect of the blue getting pushed. Somebody else is getting a blue sky, and you're just getting the little red effect of the scattering of the light. Okay, we probably had enough about that story. Looks to me close enough. We're going to stop here. I'm not even kidding this time. I'm just about done with those grades. I'm going to do all these things I keep claiming I'm going to do. So be looking for some messages from me. Until then, peace out.